we are setting out tonight on a quiet voyage. We'll explore some of the deepest questions our universe holds. For all the incredible progress that science has made, there's still an enormous amount that remains completely unknown. We've mapped distant star systems. We've measured the faint light from the cosmos's earliest moments. And we've even looked at particles that are far too tiny for anyone to ever see. Yet, with every new discovery, it seems we uncover an even deeper layer of things we don't understand. The universe really does keep its secrets well. Many of the ideas we currently rely on might just be temporary steps towards something much grander. What we think we know might be less certain than we assume. Space itself could be far stranger than our current models suggest. Time might not behave in the ways we expect. Even the fundamental building blocks of matter and energy might just be fragments of a much larger, more complete theory. Let's begin this journey through the quiet cosmic unknown. The universe likely contains regions that will always stay hidden from us. Far beyond the edges of what our instruments can possibly see, the universe stretches outwards. It expands into areas whose light will simply never reach our location. These incredibly distant regions aren't just far away, they're actually cut off from us. This happens because light has a finite speed, and because space itself is continuously stretching and expanding. Even if we could somehow build perfect tools, and then wait for an unimaginable amount of time, longer than any human lifespan, some parts of reality would simply remain forever out of reach. In these vast, unseen territories, matter could be organized into galaxies and enormous structures. These structures might never send even a single particle of light in our direction. The rules of physics, there could be exactly the same ones we know, or they might be subtly twisted in ways we have no way to verify. When we gaze up at the night sky, what we're truly seeing is just a tiny window into a much, much larger universe. We know there are countless events happening right now in those distant, hidden zones, but no one here will ever be able to witness them. It's a bit like knowing there are countless stories unfolding, but they'll forever remain untold to us. There's also a possibility that the universe contains entire realms of space where the laws of physics are completely different from our own. Many cutting-edge theories suggest that what we consider the fundamental laws of nature might not be universally fixed. Some ideas in cosmology and in fundamental physics allow for certain constants, like the masses of tiny particles or the strength of how different forces interact, to actually have different values in various parts of a much larger reality. Imagine this: in one cosmic domain, stars might never be able to ignite, simply because the conditions aren't right. In another, atoms themselves might be unstable, or entirely new kinds of matter could form, unlike anything we've ever encountered. We only really know the behavior of our own small patch of the universe. Here, the numbers just happen to support the existence of long-lived stars and the complex chemistry necessary for things like planets and life. It's totally possible that beyond our cosmic horizon, there are massive expanses where the very idea of a stable atom would be impossible to conceive of. Our familiar physics, with all its predictable rules, could simply be a local dialect. It's just one way things operate within a much grander landscape of possibilities. If that's true, then what we call fundamental might be more like a regional custom, just one example among many. And we'd have no way to actually visit the others and compare. It's a humbling thought, making us realize how limited our perspective might truly be. We still don't have a clear picture of what happened before the very first moment of time. Our best models of cosmology do a great job describing how the universe has evolved from a super hot and dense state that existed very early on. But they don't fully explain what, if anything, came before that point. In those extremely early times, both gravity and quantum physics would have been incredibly important. The problem is, we don't yet have a single, unified theory that combines these two forces in a consistent way. When scientists try to run the equations backward, they eventually stop providing meaningful answers. It's almost as if the mathematical surface of time itself just ends. Some theories suggest there might have been a phase of contraction before our current expansion. Others imagine a bounce, where the universe collapsed and then sprang back outwards. Still others describe time as emerging from something much more primitive, something that doesn't really resemble our usual ideas of before and after. We get clues about the early, hot fireball of the universe from observations of the sky. But these observations can't directly pierce whatever veil lies beyond that initial moment. The question of a true beginning might even be the wrong way for us to think about it. Yet, our minds are naturally drawn to this idea. What does it actually mean for time to start? And can there ever be a solid reason for that very first instant? It's a profound puzzle that touches on the very nature of existence. Space itself might be infinite, or it could potentially loop back on itself. When we look out into the cosmos, we can measure how space is curved over truly vast distances. However, those measurements don't yet tell us the overall, global shape of everything that exists. One possibility is that space stretches without any limits whatsoever, going on forever with no boundary and never returning to its starting point. Another idea is that space has a finite volume, but it has no edge. Think of the surface of a sphere, but in more dimensions. If you could travel far enough in one direction, you might eventually end up right back where you started. Different shapes of space would subtly alter the patterns of structures we see in the sky. But these differences are incredibly tiny and very hard to spot. Our observations so far are consistent with many different possibilities. The real shape of the entire cosmos could be much simpler or far stranger than we can currently imagine. And we may never be able to travel far enough to find out for sure. There could be invisible dimensions interwoven with the ones we experience every day. We perceive reality as having 3 dimensions of space: up, down, left, right, forward, back, and 1 dimension of time. But some theories that try to unify all the forces of nature only work if there are additional spatial directions. These extra dimensions could be curled up to sizes that are unimaginably tiny, so small that we simply don't notice them in our daily lives. Their presence might subtly affect how particles move and how gravity behaves, leaving only faint traces in experiments and our cosmic observations. In such a scenario, every single point in our familiar 3-dimensional space would actually be a tiny, multi-dimensional structure. There would be hidden paths that loop through directions our senses just can't follow. If these hidden dimensions truly exist, they might allow for entirely new kinds of particles. Or they could even connect distant regions of space in ways we've only just begun to picture. Searching for them requires incredibly creative experiments and a very careful study of how the universe has evolved. The idea that our familiar world might only be a small part of a much larger dimensional tapestry remains an open and deeply profound possibility. It means there could be far more to space than meets the eye, or even our most sensitive instruments. We also don't really know what space itself is actually made of. We often talk about space as if it's just an empty stage, a smooth background where matter moves and light travels. Yet, we don't truly understand whether that stage is a fundamental part of reality, or if it's built from something even deeper. Some approaches to quantum gravity imagine space as emerging from discrete, tiny building blocks. Perhaps it's a network of relationships, or minuscule units of area and volume that only appear continuous when you view them from far away. Others imagine space arising from patterns of quantum information. It could be like a vast web of entanglement that gives rise to the concepts of distance and geometry as collective effects, similar to how individual pixels create a continuous image. Even in ordinary physics, a vacuum isn't truly empty. It's actually filled with fluctuating fields that can give rise to real particles for brief moments. These hints suggest that the notion of a simple, empty void might be an illusion. If space has some underlying structure, then at extremely small scales, our familiar concepts of location and distance might just dissolve. They would be replaced by something that doesn't fit our usual human intuition. It's a mind-bending idea suggesting that the very fabric of our universe is far more intricate than we can currently grasp. Time might flow differently in parts of the universe we can't ever reach. Einstein's theory of relativity tells us that the passage of time isn't absolute. It actually depends on how fast you're moving and how strong the gravity is around you. Clocks that are deep within a strong gravitational field, like near a massive star, will tick more slowly compared to clocks that are far away from any strong gravity. And objects moving at very high speeds experience less elapsed time than those that are standing still. Across the universe, matter is arranged in incredibly complex ways, from dense clusters of galaxies to vast, nearly empty regions. Because of this, the rate at which time passes can vary significantly from one place to another. In distant galaxies, the rhythm of physical processes could be slightly offset from our own, even if no one there would actually notice the difference locally. In extreme environments, like very close to super, dense objects, this difference becomes even more dramatic. Outside observers would literally watch events unfold in slow motion, since we can't synchronize clocks across distances that are unreachable. We're left with a kind of patchwork of local times, all woven together by theoretical physics. The idea that there's a single, universal no becomes very difficult to maintain once we really start to consider the vastness of the cosmos. Every point in space could be experiencing its own unique temporal rhythm. The universe might just be one bubble among countless others. Certain theories of cosmic inflation suggest that the incredibly rapid expansion that happened in the early universe might not have stopped everywhere at the same time. In some regions, this expansion could have ended and cooled down, forming bubbles, where conditions stabilized enough for galaxies and stars to eventually appear. In other regions, that accelerated growth could have continued, spawning even more bubbles, each with potentially different properties. Our observable universe would then be just one such bubble, occupying a finite domain within a much larger, continuously inflating background. Other bubbles might never collide with ours. They could remain forever separated by ever-growing distances and by regions where space is still stretching at an enormous rate. Within those distant domains, physics might take on completely different forms. Or perhaps they might echo our own universe in ways we will never be able to confirm. This picture transforms what we call the universe into just one example inside a greater multiverse. It offers explanations for certain cosmic puzzles, yet it also raises even deeper questions about what truly counts as reality. It's a concept that pushes the boundaries of our imagination. There could be structures out there that are far larger than anything we can currently observe. Astronomers have already discovered massive clusters, long filaments, and vast sheets of galaxies. These incredible formations span astonishing distances, weaving what looks like a giant cosmic web throughout space. Yet, our surveys are always limited. They're limited by how far light has traveled since the very early universe. And they're limited by the parts of the sky we've actually been able to study in detail. It's entirely possible that beyond the boundaries of our current data, there are arrangements of matter that are even grander than the largest formations we know of. Perhaps these are super-structures that completely bend our assumptions about how uniform the cosmos should be. Some faint hints already challenge our expectations. For instance, there are huge alignments of galaxies that appear more coherent than standard models predict. Whether these are just statistical flukes or actual glimpses of something deeper remains uncertain. If truly colossal structures exist beyond our observational horizon, their immense gravity could influence the motion of galaxies that we can see. They would leave only indirect signs of their presence. In that sense, an unseen architecture might be quietly shaping the cosmos we are able to measure. It's a reminder that even the grandest things we see might just be components of something even bigger and more complex. We still don't know whether the universe has a definitive edge, or if it has no boundary at all. When we talk about the universe, it's natural for our minds to picture a region with some kind of border, beyond which there would be nothing. Yet, in physics, the idea of an edge to space is quite problematic. Edges usually imply that there's something outside them. One alternative is that the universe is finite in volume, but it's curved in such a way that it has no boundary. Again, think of the surface of a sphere. It has a limited area, but it doesn't have an edge you can fall off. Another possibility is that space extends indefinitely, with no edge and no outside, just more and more of the same cosmic fabric. Our observations of the cosmic background radiation and the distribution of galaxies tell us a lot about the geometry within the part of the universe we can see. But they don't conclusively answer this global question. Even our language struggles because we are trying to describe the totality of everything from within it. Whether there's a true edge, a closed shape, or infinite extent remains one of the deepest open puzzles in science. It's a question that challenges our very intuition about space. The universe might be expanding into something that we simply cannot perceive. When we measure the movement of distant galaxies, we find that space itself is stretching, carrying them farther and farther away from us. Yet, the question of what this expansion is happening into remains completely unresolved. In standard cosmology, space doesn't actually need an outside to expand. It can grow the way a pattern drawn on the surface of a balloon grows. You can focus only on the two-dimensional surface without needing to consider the air around it. Still, it's difficult not to wonder whether the fabric of the cosmos is embedded in something much larger. If such an external realm exists, it wouldn't necessarily follow the rules of our own space or time. It might not contain matter, energy, or geometry as we understand them. Our instruments are designed to measure what happens within our universe, not beyond it. As a result, any wider container would remain hidden from our view. We'd be left to infer its possibilities only through mathematics and the behavior of those distant galaxies. The true nature of this expansion remains one of the most puzzling questions in modern science, a testament to how much we still have to learn about the most fundamental aspects of reality. We still don't understand why space is so incredibly smooth on vast scales. Across billions of light years, the universe appears remarkably uniform. The temperature of the faint, ancient radiation left over from the Big Bang varies only by tiny fractions. And matter is spread out in a pattern that's far more even than one might expect. This remarkable smoothness is quite surprising. That's because regions separated by extreme distances could never have interacted with each other in the early universe. There simply wasn't enough time for light, or any other signal, to travel between them. To explain this puzzling uniformity, theories often propose a brief phase of extremely rapid growth in the very early universe. This period, known as inflation, would have allowed regions that are now far apart to originate from a very small, connected area. Although this idea fits the observational data quite well, we still don't know what actually triggered that rapid growth, how it eventually ended, or whether alternative explanations might also work. The uniformity we observe today could be carrying information about processes that occurred even before the earliest moments we can actually probe. Space may hold silent clues about a deeper mechanism that shaped the entire cosmos long before galaxies even began to form. It's like finding a perfectly smooth surface and wondering what incredible force smoothed it out. The universe could carry subtle imprints from events that happened even before its birth. The oldest light in the universe, that faint glow we just mentioned, has traveled across space for almost the entire cosmic history. While it has been studied with incredible precision, it might still contain tiny, subtle traces of processes that happened even earlier than the hot, dense state we usually describe as the universe's beginning. Certain models of cosmic evolution predict that ripples, patterns, or slight distortions might have survived from an earlier phase. These would have been carried forward as the universe expanded and cooled. These features would be extremely delicate, hidden deep within the background noise of cosmic data. They would also be very difficult to distinguish from ordinary, everyday fluctuations. If they truly exist, they could reveal information about conditions that no current experiment can ever hope to recreate. They might hint at a prior phase of contraction, or a more complex transition that came before our familiar expansion. The possibility that our universe retains the fingerprints of an earlier era invites the idea that the cosmos has a much longer and richer story than we can currently observe. It suggests a cosmic history that stretches further back than we can imagine. There may be hidden patterns within the cosmic web that we simply haven't recognized yet. When astronomers map the distribution of galaxies, they discover a sprawling, intricate network of clusters, long filaments, and enormous empty voids. This complex web looks almost like the structure of living tissue, or even neural pathways. It shows us how gravity has shaped matter on the very largest scales of the universe. Yet, we might only be seeing the most obvious layer of this structure. Deeper mathematical relationships might link the positions and motions of galaxies in ways we haven't noticed yet. Subtle symmetries could be present in the alignment of these structures, or there might be long-range correlations that require entirely new tools to detect. Even the way galaxies rotate, or how they cluster together, might follow hidden rules that have gone unrecognized for a long time. As our surveys become more detailed and precise, they may reveal unexpected organization buried deep within what currently appears to be random. Patterns like these could hint at undiscovered physics, or at very early cosmic processes that left long-lasting effects throughout the entire web of matter that stretches across the universe. It's like finding a secret code within the grand design of the cosmos. The universe might end in ways we currently cannot even imagine. Cosmology offers several possible futures for the universe, yet none of them are truly certain. If dark energy, that mysterious force, remains steady, then space will continue expanding at an ever-increasing rate. This would gradually isolate galaxies from one another until the night sky eventually grows empty and incredibly cold. If dark energy actually strengthens over time, the expansion could accelerate so dramatically that even individual atoms might eventually be pulled apart. This is a concept known as the Big Rip. However, if dark energy weakens or even reverses its behavior, the universe could slow down, halt its expansion, and then collapse back in on itself into an incredibly dense state. This might possibly lead to a new expansion, a big bounce. Other possibilities involve transitions in the underlying vacuum of space, or even changes in the fundamental physical laws themselves. Or, perhaps there are processes we haven't even formulated yet in our theories. because we can't definitively measure the future behavior of dark energy or assess the long-term stability of the vacuum, we face fundamental uncertainty about how the story of the universe will ultimately conclude. Each scenario would shape matter and time in profoundly different ways. The vast future remains an open landscape of possibilities, with each one hinting that our current cosmic era is only one chapter in a much longer narrative. There could be cycles of cosmic creation that lie far beyond our observational horizon. Some theoretical frameworks propose that the universe didn't begin with a single, unique event. Instead, it might pass through repeating phases of contraction and expansion. In such a picture, our own cosmic history would be just one part of a much larger sequence. Previous cycles could have imprinted subtle hints on the structure we observe today. While these ideas are very difficult to test, they do offer explanations for certain puzzles, like the universe's uniformity and the fine-tuning of its structure. If the universe has indeed experienced multiple cycles, then each era might inherit conditions shaped by the ones that came before it. Entire sequences of galaxies, stars, and cosmic evolution could have risen and then faded away long before our current epoch. They would leave behind very few traces, except possibly in the earliest moments of the current expansion. These cycles might continue far into the future, forming a grand, cosmic rhythm of creation and transformation. This rhythm would lie beyond our observable domain. Whether such patterns truly exist remains unknown. Yet, they provide a striking alternative to the idea of a single, one-time beginning. We don't know what actually started the rapid expansion of the early universe. Observations very strongly support the idea that the universe underwent a brief period of incredibly fast growth shortly after its earliest moments. This expansion smoothed out any irregularities and set the stage for the eventual formation of galaxies. However, the exact cause of this rapid growth remains a deep mystery. Proposed explanations include the emergence of new fields of energy, or transitions between different physical states, or even deeper mechanisms that might involve the very fabric of space itself. Each of these proposals attempts to account for the characteristics we see today in the ancient cosmic radiation and the arrangement of matter. Yet, none has been definitively confirmed, and several predict effects that are extremely subtle and hard to detect. Without a way to directly examine the conditions of that incredibly early time, we have to rely on indirect clues and very careful analysis of cosmic patterns. The true trigger of this expansion remains an open question. Understanding it may require completely new insights that unify our ideas about gravity, quantum physics, and the ultimate origin of space itself. It's a fundamental piece of the cosmic puzzle that is still missing. The universe might have extra dimensions that are curled up too small for us to detect. Some theories that aim to unify all the fundamental forces of nature suggest that, in addition to the familiar three dimensions of space we experience, there may be additional directions. These extra directions would be folded into extremely tiny, compact shapes. These compact dimensions would be far smaller than anything any current experiment can probe. They would be hidden within the very structure of each point in space. Their geometry could influence how particles behave, alter gravitational interactions, or even allow for new types of motion that simply cannot occur in ordinary three-dimensional space. While these dimensions wouldn't be directly visible, their presence might produce very small deviations in measurements from particle collisions. Or they might leave faint signatures in the early universe. Searching for these effects requires incredibly precise instruments and very creative experimental designs. If such curled-up dimensions truly exist, it would mean that our everyday experience captures only a tiny fraction of a much richer spatial environment. The universe might be built on a dimensional foundation that remains almost entirely concealed from us. It's a wild thought that we might be living in just a small slice of a much larger reality. We also don't know whether space itself emerges from something deeper. Modern research has increasingly raised the possibility that space isn't a fundamental entity, but instead arises from more basic components. In some theoretical models, the geometry of space is produced by patterns of quantum information, or it might come from networks of relationships between microscopic elements that don't resemble physical locations in any ordinary sense. Distances, directions, and even the flow of time itself could be large-scale consequences of these underlying structures. Evidence for such ideas comes from studies of black holes and quantum physics, where traditional concepts often break down, and new principles seem to link geometry with information. While these ideas are still speculative, they offer a promising route toward unifying gravity with the world of tiny particles. If space is indeed emergent, then our familiar reality might be analogous to a surface that is formed from countless unseen interactions happening at a deeper level. Understanding this deeper layer could completely change the way we think about the very fabric of the universe and the fundamental nature of existence itself. The universe could even be a projection of a more fundamental reality. Certain approaches to quantum gravity suggest that the three-dimensional world we experience might actually be encoded on a lower dimensional structure, somewhat like a hologram. In these proposals, the full richness of space and matter arises from information that is stored on a surface that has fewer dimensions than the space it describes. This fascinating concept first emerged from the study of black holes, where the amount of information needed to describe them seems to scale with their surface area rather than their volume. Extending this idea to the entire cosmos suggests that reality might have a surprisingly architectural design. While this doesn't mean the universe is an illusion, it does imply that our usual understanding of location and depth might be secondary to deeper, more fundamental principles. Experiments and observations are just beginning to test aspects of these ideas, but the question remains far from settled. The possibility that the cosmos is a projection challenges many of our intuitive notions and opens the door to completely new ways of describing the foundations of physics. It's a truly mind-bending concept that pushes the limits of what we consider real. Dark energy may be changing over time in ways we cannot yet measure. Astronomers made the groundbreaking discovery that the expansion of the universe is speeding up. This accelerating expansion is often attributed to a mysterious influence known as dark energy. Yet, we don't know whether this enigmatic force is truly constant, or if it's slowly shifting its strength over cosmic time. Our current measurements cover only a relatively narrow slice of the universe's history, so any very slow variation would be incredibly difficult to detect. If dark energy changes, it could dramatically alter the ultimate fate of the cosmos. It might strengthen, driving galaxies apart even faster until the universe becomes a cold, dark void. Or it could weaken enough for gravity to eventually slow the expansion in the distant future. It might even undergo transitions, behaving differently in past eras than it does today. The challenge lies in the fact that dark energy doesn't interact directly with matter or light. We infer its presence only through the motion of galaxies and the overall geometry of space. Subtle changes could be hiding beneath our current measurement uncertainties, waiting for more precise observations or entirely new ways of mapping cosmic history. The nature of dark energy remains one of the most profound mysteries in all of physics. Dark matter could be something entirely outside of known physics. We clearly observe the gravitational influence of an unseen mass that surrounds galaxies and shapes the large-scale structure of the universe. This invisible matter doesn't emit any light, and it doesn't interact strongly with normal atoms. While many theories try to explain it using new, undiscovered particles, another intriguing possibility is that dark matter simply doesn't belong to the familiar family of forces and interactions at all. It could arise from a sector of physics that barely touches the one we experience. In such a scenario, dark matter might have its own kinds of particles, its own motions, and its own internal processes. It could be operating in a kind of shadow framework that rarely influences ordinary matter, except through the force of gravity. This idea opens the door to entire worlds of behavior that remain completely hidden from every detector on Earth. If dark matter truly lies outside known physics, then solving its nature will require ideas that go far beyond our standard approaches. Its presence could be a crucial clue that our current view of reality captures only a fraction of what truly exists. There might be countless particles passing through us right now that we cannot yet detect. Even within the known laws of physics, a vast number of particles are constantly moving through space. Some are familiar, like neutrinos, which pass through matter with very little interaction. Others, however, may exist beyond our current understanding. These hypothetical particles could permeate the entire cosmos, drifting through planets, stars, and even living beings without leaving any detectable traces. Their interactions might be so incredibly weak, or so unusual, that they simply escape every current instrument we have. Some theorists predict particles that rarely collide with normal atoms, while others propose entities that don't fit the usual categories of matter and energy at all. The Earth might actually be immersed in a silent sea of undetected particles. These particles could be influencing cosmic evolution, yet they remain completely invisible to us. Each new generation of detectors reaches further into this hidden landscape, searching for signs in faint flashes of light, subtle vibrations, or incredibly rare collisions. The possibility that unknown particles are quietly passing through us every single moment suggests that much of reality may be hidden just beyond our reach. It's a silent, invisible ballot happening all around us. Dark matter could form structures as complex as the visible universe. Although dark matter is invisible to us, its gravity affects everything around it. Models of cosmic evolution often show dark matter gathering into vast halos that then guide the formation of galaxies. Yet, these halos might not just be simple, uniform clouds. They could contain layers, clumps, waves, or intricate patterns. These shapes would be formed by interactions within the mysterious, dark sector itself. If dark matter has its own forces or its own families of particles, it might be capable of forming structures just as varied and complex as those made of ordinary atoms. These dark structures wouldn't emit any light, but they could influence the motions of stars and gas. They could shape galaxies in ways we haven't yet recognized. Some simulations suggest that dark matter might form filaments within halos, or support long-lived patterns that affect how galaxies rotate. Discovering such structures would require incredibly detailed observations and entirely new theoretical tools. The idea that an unseen architecture coexists right alongside the visible cosmos highlights just how limited our current perspective might be. There could be an entire, dark version of the universe with its own intricate web of structure. Dark energy might interact with matter in ways we have not yet observed. Most interpretations of dark energy treat it as something that only influences the expansion of space and not the behavior of matter directly. However, some theoretical models allow for a faint, subtle connection between dark energy and the particles that make up stars and galaxies. If such an interaction truly exists, it could cause tiny shifts in the masses of particles or the strength of fundamental forces over vast periods of cosmic time. These tiny changes might accumulate across the entire history of the universe. They could leave faint patterns in the distribution of galaxies or affect the rate at which structures formed. So far, no clear evidence for such interactions has appeared. Yet, the possibility remains open because the required effects could be extremely small and difficult to detect. Future astronomical surveys that examine distant galaxies more precisely may eventually reveal signs of this hidden dialogue between dark energy and matter. If this connection exists, it would completely reshape our understanding of how the universe evolves, and it would reveal a bridge between two of its most mysterious components. There could be multiple types of dark matter hidden in plain sight. Most discussions about dark matter assume that it's composed of a single kind of particle. Yet, nature often prefers variety and complexity. Ordinary matter, for example, includes atoms, molecules, plasma, dust, and countless other forms. Dark matter might be just as diverse. Some types could be cold and slow-moving, while others might be warm and faster. And still others could potentially bind into composite objects through interactions that happen within the dark sector itself. Each type of dark matter would influence galaxy formation differently, creating a much richer and more complex landscape than most simple models predict. Because dark matter doesn't emit light, this diversity wouldn't be directly visible to us. Instead, the mixture might reveal itself through subtle features in the motion of stars or in the shapes of galaxies. Understanding such complexity would require new methods of analyzing cosmic data and entirely new theories that allow dark matter to have internal structure. The idea of multiple unseen components hints that the dark side of the universe could be far more intricate and fascinating than we currently imagine. It's not just one mystery, but many. Dark energy could hint at a deeper layer of reality that we don't yet see. The discovery of the universe's accelerated expansion forced physicists to consider that the vacuum of space contains energy with very unusual properties. This energy doesn't behave like ordinary matter or radiation. Its effects suggest that space itself has an underlying structure that influences how it stretches. Some proposals link dark energy to quantum fields that completely fill all of space, while others connect it to geometric features that emerge from deeper, more fundamental principles. If dark energy truly reflects a hidden layer of reality, then our familiar understanding of space might be only a surface-level description. The behavior of dark energy could reveal crucial information about this deeper framework. Yet, we currently lack the tools to probe it directly. Observations of distant supernovae, galaxy clustering patterns, and the cosmic background radiation provide clues. But the full picture remains quite obscure. Dark energy may be the most accessible sign we have that reality contains levels that we haven't yet uncovered. It's a whisper from the deep structure of the cosmos. Dark matter might be a shadow of processes happening in higher dimensions. Some theoretical models propose that our universe actually contains more spatial directions than we can perceive. If higher dimensions truly exist, dark matter might be an echo of processes that are occurring within them. In this view, the particles we detect only through their gravitational pull might actually be objects that are moving or interacting in directions that are unseen by our ordinary senses. Their apparent invisibility could be a natural consequence of their higher, dimensional nature. They would interact very weakly with familiar matter because they essentially occupy different slices of reality. Yet, their mass would still tug on stars and galaxies through gravity. This idea offers possible explanations for why dark matter behaves so differently from ordinary particles, and why it forms those large halos around galaxies. Detecting such effects would require looking for very small deviations in gravitational behavior, or searching for subtle signs of extra-dimensional motion. If dark matter is truly linked to higher dimensions, Discovering its nature would completely change our understanding of what space itself can be. It would open up a whole new realm of cosmic architecture. There could be entire stars made mostly of dark matter. If dark matter can clump together under gravity, it might gather in high enough concentrations to form compact objects. In some cosmological scenarios, dark matter could collapse into dense regions that behave like stars, yet without any nuclear reactions or visible light. These dark stars would be practically invisible to telescopes that rely on electromagnetic radiation. Instead, their presence might be revealed only through their gravitational influence on other things. Some theories imagine dark matter particles that can release energy through exotic interactions, allowing dark stars to shine faintly in ways we haven't yet identified. Others picture them as cold, quiet bodies drifting silently through galaxies, leaving behind only subtle gravitational footprints. Finding such objects would require incredibly precise mapping of stellar motions or careful observations of gravitational lensing. The existence of dark stars would add an entirely new category to the cosmic inventory, showing that the universe contains kinds of stellar bodies that are fundamentally different from anything we've ever seen. It would be a profound expansion of our stellar catalog. Dark matter might carry information about ancient cosmic eras. Because dark matter interacts so little with ordinary particles, it has preserved its original properties across almost the entire history of the universe. While atoms were constantly being broken apart, fused, and reshaped in stars, dark matter remained largely unchanged. Its current distribution still reflects the conditions that existed long before galaxies even formed. If we could decode its structure, we might learn about epochs that no radiation can directly reveal to us. For example, slight variations in dark matter density might reflect events in the very early universe, or even transitions that occurred before familiar particles emerged. Mapping these patterns requires incredibly detailed observations of how galaxies move within their halos and how matter clusters on different scales. Each measurement provides a subtle hint of the ancient landscape that shaped the cosmos. Dark matter serves as a quiet record keeper of eras beyond direct observation, storing information in the way it is arranged across space. It's like a fossil record, but for the entire universe. Black holes may contain regions where the very fabric of reality breaks down. When matter collapses under its own immense gravity and forms a black hole, the equations of general relativity predict that space-time curves more and more sharply towards the center. At some point, these equations indicate that the curvature becomes infinite. This isn't a sign of a literal infinity in nature, but rather a strong indication of the failure of our current theories. Near such extreme conditions, the familiar rules of space, time, and physics may simply dissolve. Quantum effects should become incredibly important there. Yet, we still don't have a complete theory that successfully unites quantum mechanics with gravity. As a result, the interior of a black hole remains one of the greatest unsolved frontiers in physics. Physical quantities that behave smoothly everywhere else may no longer make any sense within a black hole. Even the basic concept of a location could break down. This mysterious region is hidden from the outside world by the event horizon, that point of no return. No signal can carry direct information outward from there. The unknown interior remains one of the most dramatic reminders that our understanding of reality is still incomplete. A black hole's center could be something entirely different from a singularity. Although classical general relativity predicts a point of infinite density at the core of a black hole, many researchers believe that nature generally avoids true infinities. Alternative models propose that quantum effects could replace the singularity with something far more complex. Some ideas picture a region of extremely high, but finite, density, Others describe a tiny sphere where quantum pressure somehow counteracts gravity's immense pull. Still others imagine a surface where spacetime undergoes a phase transition, like water turning into ice. These possibilities all depend on how quantum gravity actually operates. And since that field remains under active development, no single answer has yet emerged. Observations of black holes don't directly reveal their centers, so indirect evidence must be used. The behavior of gravitational waves, the motion of matter very close to the event horizon, and the long-term stability of black holes might offer crucial clues. Each scenario implies a different internal structure, suggesting that black holes might contain exotic states of matter or geometry unlike anything we have studied in laboratories. It's an extreme physics lab, hidden from view. There might be paths through black holes that lead to other places. The mathematics of general relativity actually allows for solutions where black holes connect to distant locations, or even to other universes, through hypothetical bridges often called wormholes. These structures are usually unstable in theory and may collapse too quickly for anything to ever pass through them. Yet, they remain intriguing possibilities. If quantum effects somehow modify the interior, such pathways might become more stable. In certain models, a traveler attempting to cross would face enormous tidal forces and unpredictable physical conditions, making any journey purely theoretical for now. Some theories even propose that what appears to be a black hole from the outside could actually be connected to a different region that looks like a white hole from within, ejecting matter instead of absorbing it. These concepts arise naturally in the equations of gravity. Yet, we completely lack evidence to determine whether any of them correspond to real physical objects in our universe. Even so, the idea that black holes might serve as gateways hints at a cosmos that is far more interconnected than our senses currently suggest. It's a truly sci-fi concept, but rooted in real physics. Black holes could store information in ways we don't understand. A long-standing puzzle in physics concerns what happens to the information carried by matter that falls into a black hole. Quantum theory insists that information can never truly be destroyed. Yet, classical black holes appear to simply erase the details of anything that enters them. Efforts to resolve this deep contradiction have led to the idea that information might be subtly encoded in patterns on the event horizon itself. Or perhaps it's stored in quantum states of the gravitational field around the black hole. Some proposals suggest that the horizon behaves almost like a physical surface, possessing an enormous number of microscopic degrees of freedom that can hold information. Others propose that information is released very slowly through faint radiation emitted during the black hole's incredibly long lifetime. None of these ideas are fully proven, and each one raises new questions about how information is actually represented in spacetime. The eventual resolution of this puzzle could reveal a much deeper connection between quantum theory and gravity. It would show us how the universe preserves its history, even in the most extreme and enigmatic environments. There might be tiny primordial black holes scattered throughout the cosmos. In the very early universe, density fluctuations could have been large enough in some regions to collapse directly into small black holes. These, primordial, objects wouldn't have formed from collapsing stars. So, their masses could range from extremely small, even microscopic, to quite large. If they truly exist, they might contribute to the mysterious dark matter or influence cosmic evolution in subtle ways. Some might have evaporated completely through Hawking radiation, while others could still drift silently through galaxies, completely invisible to us. Their presence might be revealed through gravitational lensing of distant stars, or through disruptions in the motions of other objects, or perhaps even through faint radiation produced during their final stages of evaporation. Despite very careful searches, no confirmed detection of these primordial black holes has yet been made. The possibility of primordial black holes remains open, offering a crucial link between the physics of the early universe and the persistent dark matter puzzle. If they are real, they would provide a direct window into the incredibly extreme conditions that existed long before the very first stars ever formed. We don't know what happens at the very edge of a black hole. The boundary that separates the interior of a black hole from the outside universe is called the event horizon. It's not a solid surface you could land on, but rather a region in spacetime where escape becomes absolutely impossible, even for light. While general relativity predicts how this horizon behaves, quantum effects really complicate the picture. According to quantum theory, the horizon should emit radiation due to quantum processes, a phenomenon known as Hawking radiation. Yet, the detailed mechanism behind this remains unclear. Some research suggests that the horizon might actually have a complex structure, influenced by quantum information. Others picture it as a smooth, featureless boundary. Because we can't observe the horizon up close, our understanding relies heavily on theoretical models. The behavior of particles, light, and information near this boundary may hold vital clues about the ultimate unification of physics. The edge of a black hole is a true frontier where known laws reach their absolute limits, making it a key area of study for anyone seeking a deeper understanding of gravity and quantum mechanics. It's the ultimate cosmic boundary. Black holes could evaporate in ways we have never observed. Quantum theory predicts that black holes emit radiation, slowly losing mass over incredibly long timescales. This process, while theoretically robust, has never been directly observed. That's because even small black holes evaporate far too slowly for our current detectors to pick up. Some models suggest that this evaporation might include sudden bursts of energy or changes in the spectrum of the emitted radiation, particularly in the very late stages of the black hole's life. Others propose that the final moments of a black hole's existence could reveal entirely new physics, perhaps involving exotic particles or transitions in the very nature of spacetime. If black hole evaporation proceeds differently from the standard theoretical picture, it could dramatically alter our understanding of energy conservation, information preservation, and the entire life cycle of black holes. Detecting these faint signals would require either an unexpectedly small black hole appearing very close to Earth, or entirely new methods for observing extremely faint radiation across the vast cosmos. The final fate of black holes remains an open question, one with profound implications for the very nature of the universe. Some black holes might have formed even before the first stars existed. Most black holes we know about arise from massive stars collapsing at the end of their lives. However, conditions in the very early universe may have allowed black holes to form directly from incredibly dense regions of primordial gas. These, first-generation, black holes would predate the first stars and galaxies. They could have acted as crucial seeds that influenced early cosmic structure. Their growth could help explain how some supermassive black holes became so enormous so quickly, which is an ongoing puzzle in astronomy. These early black holes might have interacted with the surrounding gas, altering the rate at which the first stars eventually formed. Observations of ancient quasars already reveal extremely massive black holes existing at times when the universe was still incredibly young. Understanding how these cosmic giants arose may require the existence of an even earlier generation of black holes, formed through mechanisms completely unrelated to stellar evolution. These ancient objects would provide invaluable insight into the earliest chapters of cosmic history, truly pushing back the timeline of black hole formation. Black holes could shape the universe more profoundly than we currently realize. While black holes are often pictured as isolated, destructive objects, their influence actually extends far beyond their immediate surroundings. The largest galaxies, for example, appear to have enormous black holes, millions or even billions of times the mass of our Sun, right at their centers. The incredible energy released by matter falling into these giants can dramatically shape the growth of the entire galaxy. Powerful jets of high-energy particles can heat or disperse vast amounts of gas, regulating star formation across enormous regions. Even smaller black holes can influence their environments by triggering bursts of radiation or stirring the motion of nearby matter. On truly cosmic scales, the collective activity of countless black holes may affect how large structures evolve, how galaxies cluster together, and how gas circulates between different regions. These effects, while often indirect, can completely reshape entire regions of space over immense periods of time. The full role of black holes in cosmic evolution is still being uncovered, hinting that they are not merely the endpoints of stellar life, but powerful engines that drive large-scale transformations throughout the universe. There may be hidden black holes that emit almost no light at all. Most known black holes are discovered because of the intense radiation produced by superheated gas spiraling into them. However, many black holes may exist in very quiet environments, where very little matter actually falls inward. These objects would be almost completely dark, detectable only through their subtle gravitational pull on other things. Some may drift through space alone, completely unbound. Others may reside in the outskirts of galaxies or within dense star clusters. Finding them requires incredibly careful analysis of stellar motions, or observations of gravitational lensing, or very rare interactions with surrounding objects. The universe could contain far more black holes than our current observations suggest, with many remaining completely invisible to us. These silent black holes hold crucial clues about stellar evolution, galactic dynamics, and the unseen population of cosmic remnants scattered throughout the cosmos. Their existence reminds us that much of the universe may be made of objects that reveal themselves only through subtle gravitational effects. It's a universe full of silent, invisible giants. Gravity might behave differently on scales larger than galaxies. Astronomers have measured gravity with incredible precision within our solar system and even inside individual galaxies. Yet, on the truly vastest scales of the cosmos, it becomes far more difficult to determine whether the familiar equations of gravity still apply exactly. The motion of galaxies within massive clusters, the rate at which large cosmic structures grow, and the intricate pattern of ancient cosmic light all depend on gravity acting across immense distances. Some observations hint at slight mismatches between theoretical predictions and the reality we observe. This suggests that gravity might subtly change its behavior when stretched over enormous scales. These variations could be tiny, yet influential enough to affect the overall expansion of the universe or the formation of cosmic structures. Several ideas propose that gravity may weaken, strengthen, or even shift its fundamental form when dealing with the emptiest regions of space. Others suggest that modifications might occur because the universe isn't perfectly uniform. Untangling these possibilities requires deeper surveys, more refined models, and entirely new ways of testing gravity across cosmic landscapes far larger than anything accessible in our laboratories. It's a challenge to the very foundation of how we understand forces. There could be hidden forces acting across cosmic distances. In addition to gravity, the universe may host other long-range forces. These forces might barely affect everyday matter, but they could subtly shape the cosmos in profound ways. These hypothetical forces could influence how galaxies move or how galaxy clusters evolve. They might act extremely weakly, making them difficult to detect within our solar system yet powerful and influential across billions of light years. Some theories predict that these forces emerge from new fields that completely fill all of space. They might guide the behavior of dark matter or interact with ordinary matter only through very delicate channels. Such forces could help explain unusual motions within galaxies or unexpected patterns in cosmic structure. Detecting them would require incredibly precise observations of distant objects, careful comparison with theoretical predictions, and a willingness to consider that the universe might include influences far beyond the familiar four fundamental interactions we currently know. If these hidden forces truly exist, they would reveal an enriched and far more intricate picture of cosmic behavior, adding entirely new layers to the universe's dynamic processes. Gravity might be linked to quantum information in a way we don't yet see. Ideas from quantum theory and general relativity are increasingly suggesting that spacetime itself might be fundamentally connected to the flow of information. In some approaches, the very curvature of space could emerge from the structure of microscopic quantum states. Gravity would then arise as a large-scale consequence of how information is organized. This perspective connects the bending of light, the motion of planets, and the behavior of black holes to deeper patterns involving quantum entanglement and quantum correlations. If this link is real, then classical gravity, as we know it, might just be the visible expression of an underlying informational fabric. Evidence for these ideas comes from studies of black hole thermodynamics and from mathematical correspondences between geometry and quantum systems. Yet, no direct experiment has confirmed this connection. Understanding it may require entirely new tools that can bridge the enormous gap between quantum physics and gravity. This possibility hints that the universe's geometry may not be fundamental, but instead a reflection of hidden informational rules that govern reality at its deepest level. The universe could contain gravitational phenomena we haven't even imagined. Most of our understanding of gravity comes from observing planets, stars, black holes, and large-scale structures. Yet, the universe is vast enough that phenomena completely unknown to us may occur under extreme conditions, or in regions we simply haven't explored yet. There might be exotic gravitational configurations where spacetime behaves in ways not described by simple curvature. Strange objects could exist that bend space in asymmetrical or unpredictable patterns. Regions with unusual forms of matter might produce entirely new gravitational effects that have left only faint or indirect signs in our observable data. As our instruments improve, we may uncover hints of these unfamiliar behaviors, perhaps in gravitational wave signals or in anomalies found in the distribution of distant galaxies. The full diversity of gravitational possibilities may extend well beyond our current theories, waiting to be discovered in the deep, unexplored reaches of the cosmos. It's a reminder that gravity itself might hold more surprises than we can predict. There might be regions where gravity temporarily weakens or strengthens. The strength of gravity is usually treated as a constant, unchanging force. Yet, in some theoretical frameworks, it could vary slightly across time or space. These variations might arise from fields that evolve slowly across cosmic distances, or from interactions between gravity and unknown components of the universe. If gravity fluctuates gently, these changes would be far too small to notice here on Earth, but they could profoundly influence cosmic evolution over immense periods. Regions where gravity is slightly stronger might form structures earlier, while weaker regions might delay the growth of galaxies. Observations of distant galaxy clusters and the cosmic web may hold subtle signs of such variations. Distinguishing them from ordinary cosmic variability is incredibly challenging, requiring careful analysis of enormous datasets and sophisticated computer simulations. If gravity does shift in strength, even by tiny margins, It would imply a deeper and more dynamic foundation underlying one of nature's most familiar forces. It would mean gravity is not quite as fixed as we once thought. Gravity could actually leak into dimensions beyond our own. Some theories propose that gravity might not be confined to the familiar three-dimensional space we inhabit. Instead, it could spread into additional spatial directions that are hidden from our ordinary perception. If this were true, gravity would appear weaker than expected in our three-dimensional world, because part of its influence would extend into these unseen directions. This intriguing idea could help explain why gravity is so much weaker than all the other fundamental forces. It might also produce distinctive patterns in experiments designed to detect tiny deviations from Newtonian behavior, which is our classical understanding of gravity. On cosmic scales, gravity leaking into higher dimensions could influence the rate at which structures grow, or even contribute to the accelerated expansion of the universe. While no conclusive evidence has been found, the possibility remains compelling because it integrates naturally with theories that attempt to unify all the fundamental interactions. Discovering extra-dimensional effects would completely reshape our understanding of space, matter, and the fundamental behavior of the cosmos. The gravitational constant might not be constant everywhere. The constant that sets the strength of gravity plays a central role in every astronomical calculation we make. Yet, we don't know whether it is truly fixed across all of space and all of time. If it varies even slightly, it could influence the formation of stars, the behavior of galaxies, and the entire evolution of the universe. Subtle shifts might occur due to interactions with unknown fields, or due to processes that began in the very early universe. Observations of distant objects offer indirect tests for this idea. Yet, distinguishing true variation from ordinary astrophysical differences is extremely challenging. Some studies have searched for signs in the precise timing of pulsars, the brightness of distant supernovae, or the distribution of galaxy clusters. So far, the results remain inconclusive. If future measurements reveal that the gravitational constant actually changes, it would indicate that gravity is not a simple, universal force, but rather a dynamic quantity shaped by deeper layers of physics. It would add a surprising twist to a seemingly fundamental number. The way gravity works near the very beginning of time is still unknown. As we trace cosmic history backward, conditions become increasingly extreme. Temperatures rise dramatically, densities climb to unimaginable levels, and quantum effects become incredibly significant. Under such circumstances, general relativity alone cannot accurately describe gravity. We desperately need a theory that unifies gravity with quantum physics. Yet, that complete theory remains unfinished. Without it, we cannot fully understand how space curved or how matter behaved during the earliest moments after the universe's beginning. Clues may be hidden in the precise pattern of ancient cosmic light, in the distribution of large-scale structures, or in the subtle behavior of gravitational waves. These hints suggest that gravity may have operated quite differently at that time, perhaps allowing for phenomena that no longer occur today. The early universe represents a unique laboratory with conditions impossible to recreate here on Earth. Understanding gravity in that extreme environment remains one of the most pressing challenges in modern cosmology. It's the ultimate frontier for theoretical physics. There could be particles that mediate gravity in subtle ways. In quantum field theory, fundamental forces are often transmitted by tiny particles. If gravity follows a similar pattern, it might be mediated by a hypothetical particle called a graviton. Such a particle would interact extremely weakly, making it nearly impossible to detect in experiments here on Earth. Its existence could influence gravitational waves, modify the behavior of black holes, or subtly affect how matter clusters on large scales. Some theories predict entire families of such particles, each contributing in different ways to the overall behavior of gravity. Detecting them would require methods capable of isolating incredibly faint signals, or observing effects that accumulate over vast cosmic distances. These particles may also interact with unknown fields or dimensions, further complicating their behavior. If they exist, they would provide a direct route toward unifying gravity with quantum theory, revealing the microscopic structure behind the very force that shapes the cosmos. It would be a monumental discovery, showing us gravity's smallest components. Gravity might arise from something deeper than space-time itself. The familiar picture of gravity as the curvature of space-time, as described by Einstein, may actually be an approximation of a more fundamental process. In some models, gravity emerges from the collective behavior of microscopic constituents that don't resemble space at all. These constituents could be quantum bits of information, relational structures, or other entities that operate according to rules unlike any classical theory. Spacetime itself would then be a large-scale, emergent phenomenon, much like temperature arises from the collective motion of countless microscopic atoms. If gravity is emergent, then understanding its true nature requires identifying these underlying components and the principles that govern them. Evidence for this idea comes from deep connections between thermodynamics, information theory, and black hole physics. Although still speculative, this concept offers a unified way to link gravity with quantum mechanics. It suggests that our very sense of space, time, and curvature may be secondary effects, shaped by an unseen foundation that determines how the universe behaves at its deepest, most fundamental level. The first stars may have been unlike anything in the modern universe. Astronomers believe the earliest stars formed from pristine gas, containing only hydrogen and helium. These were the simplest elements created in the first few minutes of cosmic history. Without heavier elements to cool the gas efficiently, these stars may have grown far more massive than anything that typically forms today. Some theories suggest that they reached hundreds of times the mass of our Sun, burning at extraordinary temperatures and living for only very brief periods before collapsing into black holes or exploding as supernovae. Their incredibly hot interiors may have produced the very first heavy elements, seeding later generations of stars and profoundly shaping the chemical composition of the universe. Because these earliest giants lived fast and died young, they vanished long before any galaxy reached maturity. Detecting traces of them requires studying faint signals imprinted on ancient cosmic light, or observing extremely distant galaxies where their influence remains embedded in the distribution of gas. The precise nature of these first stars, often called population-Arcturine stars, remains unknown. Yet, they set the stage for everything that followed, initiating the cosmic cycle of creation. We don't know how the first galaxies formed so quickly. When powerful telescopes peer back into very early cosmic times, they reveal galaxies that appear surprisingly mature, despite the relatively short interval since the first stars ignited. These early galaxies contain structured regions, vigorous star formation, and sometimes even central black holes that are already quite massive. Standard models predict that assembling such complex systems should require longer periods than the universe appears to have given them at that early stage. This mismatch has prompted renewed study of how gas collapses, fragments, and ignites under primordial conditions. It also raises important questions about whether our theories correctly describe how matter behaved during the first few 100 million years after the Big Bang. New observations continue to find surprisingly bright and organized early galaxies, deepening the puzzle even further. These discoveries hint that early cosmic environments may have fostered rapid growth through processes not yet fully captured in our simulations. The first galaxies remain key to understanding how the large, scale structure of the universe eventually emerged from initial tiny fluctuations. Some ancient galaxies look far older than they should be. Observations of extremely distant galaxies sometimes reveal systems that appear too massive, too bright, or too chemically enriched for their apparent age. These galaxies formed when the universe was still in its infancy, only a few 100 million years old. Yet, they display properties that are expected of far later epochs. Their stars can show signs of earlier generations, even though there shouldn't have been enough time for multiple cycles of star formation and evolution to occur. This tension challenges our current models of galaxy growth, prompting scientists to examine whether star formation was more efficient in early cosmic conditions or whether unknown mechanisms accelerated their development. Some of these galaxies may have undergone rapid mergers, while others may have collapsed unusually quickly from dense pockets of primordial gas. Each explanation carries significant implications for cosmology, suggesting that our current picture of early cosmic timelines may need refinement. These ancient outliers remain compelling markers of unexplained processes that shaped the earliest structures in the universe. There could be stars made almost entirely from exotic particles. Most stars shine through the nuclear fusion of familiar elements like hydrogen and helium. But some theories propose the existence of stars composed partly or entirely of exotic forms of matter. These hypothetical objects might use dark matter interactions as an energy source, or they might consist of particles that don't follow the usual rules of nuclear physics at all. If such stars exist, they would behave very differently from ordinary ones. Their temperatures, their lifetimes, and their internal structures could diverge dramatically from our standard expectations. They might emit unusual spectra of light or produce neutrino signatures unlike any known stellar process. Detecting them would require careful searches for stars that appear too dim, too bright, or too stable for their observed mass and age. These exotic stars would offer direct insights into unfamiliar physics, showing that starlight may not always come from the same kinds of processes that power the familiar cosmos we see every night. It would be a new kind of stellar engine. We don't know how supermassive black holes grew so fast. Giant black holes, millions or even billions of times the mass of our Sun, exist in galaxies throughout the universe. Yet, observations clearly show that some of these giants were already enormous when the universe was still very, very young, only a few 100 million years old. Their rapid growth poses a significant challenge because known processes of accretions, where gas falls onto the black hole and merging with other black holes, don't seem efficient enough to build such massive objects so quickly. Several ideas attempt to resolve this puzzle. Some propose that the very first black holes formed from stars far larger than any seen today. Others suggest that entire clouds of gas may have collapsed directly into black holes without forming stars first. Another possibility is that early cosmic environments allowed unusually rapid feeding rates for these black holes. Each explanation requires conditions that differ significantly from those found in the modern universe. Understanding how these cosmic giants emerged so early is essential because they profoundly influenced the evolution of the first galaxies and shaped large-scale cosmic development. Some galaxies appear to lack dark matter for reasons we cannot explain. Dark matter is generally thought to be absolutely essential for galaxy formation, providing the crucial gravitational framework that holds stars and gas together. Yet, a handful of observed galaxies seem to contain far less dark matter than expected, and in some rare cases, almost none at all. Their stars move more slowly than predicted by models that include dark matter, suggesting that dark matter doesn't dominate their mass. These unusual systems challenge widely accepted ideas about how galaxies form and evolve. Some hypotheses propose that strong interactions with neighboring galaxies stripped away the dark matter, while others suggest that these galaxies may have formed through processes not yet understood. Observing them more closely may reveal whether they truly defy our expectations, or whether hidden complexities in their structure mask the presence of dark matter. These galaxies remain rare, but incredibly important, offering unexpected insights into the diversity of cosmic evolution and the mysterious role of dark matter. There could be entire galaxies made mostly of invisible matter. While some galaxies appear to lack dark matter, others might be composed almost entirely of it. Such dark galaxies would contain very few stars, making them extremely faint and incredibly difficult to detect. Their presence could be inferred only through their gravitational effects on nearby objects, or through subtle gravitational lensing of background light. If these dark, dominated galaxies exist, they might account for a portion of the missing matter in the universe and provide crucial clues about how dark matter behaves on galactic scales. They might form in regions where normal matter couldn't cool efficiently, or where star formation was somehow suppressed. Studying them would deepen our understanding of how structure forms in the dark sector and how galaxies assemble under a wide range of initial conditions. Discovering even a few of these would dramatically expand our view of what truly counts as a galaxy. It would introduce a whole new class of cosmic structures to our inventory. There might be stellar objects that don't fit into any known category. Astronomers classify stars into familiar groups based on their temperature, mass, and chemical composition. Yet, astronomical surveys occasionally reveal objects that completely defy simple categorization. Some appear too cool to be considered stars, but too warm to be planets. Others show chemical signatures or brightness patterns that don't match our standard models at all. These oddities may represent previously unknown stages of stellar evolution or entirely new kinds of objects shaped by exotic physical processes. They could be remnants of unusual formation histories or products of environments not seen anywhere else. Understanding them requires detailed observation and creative thinking about how matter behaves under unexpected conditions. Each new anomaly challenges the boundaries of our established classifications, reminding us that the universe may host forms of stellar structure that are rare, fragile, or simply unfamiliar to us. It's like finding a creature that doesn't fit into any known biological taxonomy. There could be ancient cosmic structures we haven't yet seen. The observable universe contains clusters, filaments, and other large-scale formations. But our surveys cover only a limited portion of the cosmos. Beyond the reach of current instruments, there may be structures that are older, larger, or more complex than any we have mapped so far. These might include massive collections of galaxies, unusually shaped regions of cosmic voids, or patterns imprinted by early processes that no longer operate today. Some features may be so faint or diffuse that they blend into the background noise, while others may lie beyond our observational horizon completely. As telescopes and analysis techniques continue to improve, we may uncover hints of these hidden structures through their gravitational effects, subtle distortions of ancient light, or unexpected alignments of visible galaxies. Their discovery would deepen our understanding of how matter arranged itself across vast cosmic time, revealing an even richer history for the universe's grand architecture. Some stars may collapse in ways we don't understand. Most stars follow predictable paths from their formation to their final, dramatic collapse. Yet, some observations reveal stellar deaths that don't match our standard explanations. Certain stellar explosions appear either too bright or too faint for their expected mass. Others produce unusual remnants or emit energy in ways that challenge known physics. Some stars may collapse directly into black holes without any visible explosion at all, while others may undergo partial collapse that leaves behind exotic cores. These anomalies suggest that the internal processes driving stellar endings may involve complexities not fully captured in our current models. Studying such events requires rapid, coordinated observations, broad wavelength coverage, and careful comparison with theoretical predictions. The diverse ways in which stars reach their final moments reveal that stellar evolution still contains many unsolved mysteries, showing us that the life cycle of a star can be far more varied and surprising than we thought. Neutron stars might hide states of matter unknown on Earth. Inside a neutron star, matter is compressed to densities far beyond anything achievable in laboratories here on Earth. Under such extreme conditions, atoms no longer exist in their familiar forms. Electrons are forced into protons, forming an immense sea of neutrons packed together with almost no empty space between them. Yet, even this description may be too simple. The pressure in the core could become so extreme that neutrons themselves break down into their constituent quarks, or rearrange into entirely new states of matter. Some models predict a fluid of quarks, while others imagine strange particles that appear only under the most intense compression. These extreme environments may host behaviors not found in any other place in the universe. Because we cannot probe neutron star interiors directly, we rely on clues from their vibrations, their cooling patterns, and the way these stars react when paired in binary systems. Each observation offers a hint. Yet, the true nature of matter inside remains an unsolved and profoundly compelling mystery. It's a window into the most extreme states matter can achieve. There could be objects denser than neutron stars, but not quite black holes. The known universe contains white dwarfs, neutron stars, and black holes as the final stages of stellar evolution. But some theories suggest the existence of objects that fall between the last two categories. These hypothetical bodies could be composed of exotic particles or unusual arrangements of matter that resist complete gravitational collapse, even at extreme densities. They might be smaller and heavier than ordinary neutron stars, yet not compressed enough to form an event horizon, the point of no return for a black hole. If such objects exist, they would challenge our understanding of the nuclear forces that hold matter together. Their unique signatures might hide in puzzling mass measurements or unusual behaviors observed in binary star systems. Distinguishing them from known objects requires incredibly precise observations of how they bend light and how they interact with companion stars. These ultra-dense bodies would provide a natural laboratory for physics beyond the familiar, revealing new layers of complexity in how matter behaves under pressures far surpassing anything seen on Earth. It's a missing rung on the ladder of cosmic density. Some neutron stars might convert entirely into exotic matter. As certain neutron stars gain mass, either through accreting material from a companion star or by evolving over long timescales, their internal pressure may reach critical thresholds where the neutrons themselves become unstable. In some theoretical models, this instability triggers a sudden conversion to strange matter, or quark matter, creating an object radically different from its original form. This transformation could occur suddenly or gradually, altering the star's rotation, its magnetic field, and its thermal properties. If the entire interior converts, the star effectively becomes a new type of compact object with a different density and structure. Detecting such transitions would require careful monitoring of pulsars for abrupt changes in their timing or unexpected shifts in their emitted radiation. These conversions, if real, would reveal that nature supports forms of matter more exotic and unpredictable than anything observed in laboratories here on Earth. The idea that a neutron star can transform from one extreme state to another adds a remarkable dimension to the study of compact objects, showing us matter's incredible plasticity. There could be planets orbiting neutron stars that, by all accounts, shouldn't exist. The discovery of planets around neutron stars came as a huge surprise to astronomers. That's because the violent events that create these compact stellar remnants, supernova explosions, should destroy or eject any nearby worlds. Yet, several pulsars, which are rapidly spinning neutron stars, host planets that orbit steadily, suggesting either remarkable survival skills or formation from the debris. After the original star's explosion, these planets experience intense radiation and extreme gravitational conditions, making them unlike typical worlds orbiting ordinary stars. Some may have formed from disks of material shed during the supernova, while others may be remnants of disrupted companion stars. Their unusual origins raise profound questions about how planets can form or endure in such hostile environments. Studying them allows researchers to explore the outer limits of planetary physics and examine worlds shaped by conditions far removed from those that influenced our own solar system. These strange planetary systems highlight the incredible resilience and diversity of planetary formation across the cosmos. Neutron star collisions might produce unknown particles. When two neutron stars spiral together and eventually merge, they create some of the most extreme conditions in the entire universe. Temperatures soar to incredible heights, and densities climb to unimaginable levels. This produces an environment where nuclear reactions and particle interactions reach energies far beyond those achievable in even the most powerful particle accelerators on Earth. Such collisions might generate particles that simply don't appear in ordinary reactions, revealing aspects of physics that remain hidden in normal cosmic conditions. These incredibly violent events also produce gravitational waves and powerful bursts of radiation that can carry subtle information about the particles involved. If unknown particles are created, they might affect the distribution of energy or alter the signatures observed by our telescopes. Each merger offers a rare opportunity to study matter at its most extreme, providing crucial clues about the behavior of fundamental particles under conditions that it existed only very briefly in the earliest universe. It's a natural particle accelerator on a cosmic scale. Some neutron stars spin in ways that defy current physics. Neutron stars are well known for their incredibly rapid rotation, yet some exhibit spin rates or timing behavior that challenge our current theoretical expectations. Certain pulsars maintain astonishingly stable periods for long stretches, while others glitch, suddenly changing their rotation speed in unpredictable jumps. A few even spin so incredibly fast that their very survival seems to defy the limits imposed by structural integrity, suggesting they should tear themselves apart. These behaviors may involve complex interactions among the star's incredibly dense crust, its superfluid interior, and its powerful magnetic fields. They might also hint at processes not yet fully understood, such as interactions with exotic matter or instabilities rooted in quantum phenomena. Observing these precise spin patterns helps researchers test models of how compact objects evolve and how their internal layers interact. The sheer diversity of rotational behaviors suggests that neutron stars may host intricate mechanisms that push the boundaries of known physics, making them fascinating, rapidly spinning puzzles. There could be pulses of neutron star activity we have never detected. Neutron stars emit radiation across a wide range of wavelengths, and much of this emission is highly directional, like a cosmic lighthouse beam. If their beams don't sweep across Earth, we simply never observe their signals. Many neutron stars may therefore remain completely unknown, hidden simply because their emission doesn't intersect our line of sight. In addition to regular pulses, neutron stars can produce bursts, flares, or subtle vibrations that may be too faint or too brief for current instruments to capture. Some phenomena may require entirely new detectors or more sensitive surveys to uncover. There might be entire classes of neutron star emissions that lie just outside the capabilities of our existing technology. Detecting these would greatly expand our understanding of how neutron stars transfer energy, how their magnetic fields evolve, and how their interiors respond to immense stress. The unseen behaviors of these compact objects likely form a rich and unexplored domain of astrophysics, a hidden symphony of cosmic activity. Neutron stars might hold clues about the universe's earliest moments. Because neutron stars contain matter compressed to densities similar to those present shortly after the very beginning of the universe, studying them offers unique insights into physical conditions that no laboratory on Earth can replicate. Their cores may preserve information about interactions that shaped the early cosmos, including transitions between different states of matter. The behavior of their crusts, their magnetic fields, and their oscillations reflects fundamental forces that also influenced early cosmic evolution. Observations of neutron stars in binary mergers provide crucial data about how matter behaves at extreme temperatures and densities, echoing conditions from the first fractions of a second of cosmic history. By carefully decoding the signals from these violent events, scientists hope to learn about forces and particles that operated in the earliest moments. Neutron stars serve as natural time capsules, holding information from epochs that are otherwise completely inaccessible to us. They are a tangible link to the universe's infancy. Some neutron stars might be slowly transforming into black holes. As neutron stars age or accumulate matter from companion stars, they may gradually approach the critical threshold at which gravity finally overcomes all internal pressure. When this limit is crossed, the star can collapse into a black hole. This transformation may not occur abruptly. Some models suggest a gradual sequence of internal changes as the star becomes increasingly compact, with phases marked by shifts in its rotation, magnetic fields, or emission properties. Observing these subtle signatures might allow astronomers to actually witness the stages leading to collapse. Such transitions would reveal the fine boundary between the stability of neutron matter and the irresistible gravitational pull that forms a black hole. Identifying stars on the very brink of this transformation would provide invaluable information about the fundamental limits of matter and the complex pathways that lead to the creation of black holes. It's like watching a slow motion cosmic metamorphosis. Neutron star crusts could contain the strongest material in the entire universe. The outer layers of a neutron star form an incredibly dense, crystalline lattice of nuclei packed together under extreme pressure. This material must support enormous magnetic fields and withstand immense stresses caused by the star's rapid rotation and internal motions. Calculations suggest that this crust structure may be hundreds of times stronger than any known substance on Earth. It could deform without breaking, endure intense strain, and store vast amounts of elastic energy. When this crust finally gives way, it may produce sudden changes in rotation, known as glitches, or powerful bursts of radiation. Understanding the properties of this remarkable material helps explain how neutron stars behave under stress and why they sometimes experience abrupt shifts. Its incredible strength reflects the unique conditions of these compact objects, where extreme density and pressure create forms of matter that simply cannot exist anywhere else in the cosmos. It's truly a cosmic super material. We still don't know what most comets actually originate from. Comets carry some of the most ancient and pristine material in our solar system. Yet, their true origins remain elusive and largely unknown. While many are believed to come from a distant reservoir known as the Oort cloud, we have never directly observed this region. It lies so incredibly far from the Sun that any objects within it reflect almost no light, making them effectively invisible to even the most powerful telescopes. The few comets we do see are those that have been nudged inward by subtle gravitational disturbances. But these represent only a tiny sample of what likely exists out there. Their compositions vary widely, hinting at different birthplaces or different histories. Some contain ingredients associated with incredibly deep, cold environments, while others show signs of processing in warmer regions. This diversity suggests that comets may form in multiple zones or migrate long distances before settling into the far reaches of the solar system. Until we develop ways to detect objects across those extraordinary distances, most of their place of origin will remain a hidden chapter of our solar system's story. There could be entire clouds of objects beyond the reach of our telescopes. Astronomers suspect that the very outskirts of planetary systems, including our own, may hold vast collections of icy bodies. These collections could be far larger in number than all the comets and asteroids we observe closer to the Sun. These distant clouds could contain trillions of small objects, drifting silently and unseen through space. Because they reflect so little light and lie at such immense distances, they evade even the most powerful telescopes we have. Their existence is inferred from the behavior of long-period comets and from theoretical models of how planetary systems form. These unseen populations may include bodies with diverse compositions, shapes, and histories, each one shaped by conditions in the early solar nebula. They could also subtly influence the motion of nearby stars or record faint gravitational interactions from ancient encounters. Detecting them will require future missions that can sense faint thermal signatures or gravitational effects across enormous distances. Until then, the outermost regions of planetary systems will remain among the least explored realms in astronomy. The space between stars may hold far more than just dust and gas. Interstellar space is often described as a very thin mixture of dust, gas, and radiation. Yet, growing evidence suggests that it may contain far more complexity than we initially thought. Observations of absorption lines in starlight and faint emissions reveal unexpected molecules, unusual temperature gradients, and hints of structures that don't fit simple models. Some regions appear to host dense clumps of material that drift independently, while others contain magnetic patterns that extend for great distances. There may also be charged particles and tiny grains with properties distinct from those found in our solar system. These components influence how light travels through space, how stars gather material, and how shock waves from supernovae propagate. The interstellar medium is incredibly dynamic, constantly shaped by stellar winds, radiation, and passing clouds. Understanding it requires combining chemistry, plasma physics, and detailed studies of cosmic dust. Far from being empty or simple, the space between stars may be a vibrant, evolving, and highly complex environment. It's a cosmic ocean with hidden currents and unexpected inhabitants. There could be invisible structures moving through interstellar space. As astronomers map the galaxy, they sometimes find variations in starlight that hint at objects or patterns passing between us and distant stars. These features don't match the behavior of known clouds of gas or dust. Some appear transient, shifting on timescales too short for ordinary interstellar material to explain. Others produce effects that suggest large but diffused structures with properties unlike typical gas or dust formations we're familiar with. These invisible shapes might be composed of extremely fine particles, long magnetic filaments, or low-density material that interacts with light in unusual ways. They could form naturally through cosmic turbulence or arise from processes not yet understood. Detecting them requires repeated observations of the same stars and very careful analysis of these subtle changes. If such structures are common, they may influence how matter cycles through the galaxy shaping star formation and the distribution of interstellar material. Their elusive nature highlights how much remains undiscovered in the vast, seemingly empty spaces between stars. It's a silent, unseen architecture shaping galactic flow. Some rogue objects traveling through space defy easy classification. Occasionally, astronomers detect objects moving on trajectories that simply don't match those of typical comets, asteroids, or planets. These rogues drift freely through space, completely unbound to any particular star. Some may be fragments from planetary systems that were disrupted long ago, while others might have formed independently in the cold, dark depths between stars. Their properties vary widely. A few show comet-like activity when approaching a star, while others behave more like dense, rocky bodies. Some move at speeds that suggest very distant or tumultuous origins. Because they don't remain in our solar system for long, studying them requires rapid observation and very careful analysis. These interstellar visitors offer unique insights into the diversity of material present in the galaxy and the powerful processes that can eject objects from planetary systems. Their unusual features challenge existing astronomical categories and reveal that the galaxy may hold many forms of wandering bodies we have only just begun to identify. Interstellar space may contain huge reservoirs of frozen, ancient material. Cold regions far from the heat of stars allow molecules and dust grains to survive unchanged for immense periods of time. These reservoirs could hold frozen gases, complex organic compounds, and minerals that are older than many of the stars in our galaxy. When such material is disturbed by shock waves from supernovae or by passing objects, fragments may drift into denser regions, influencing the formation of new stars and planets. Some of this frozen material may carry unique signatures of chemical processes that occurred in the earliest phases of the galaxy's life. These reservoirs also affect the temperature and ionization of interstellar clouds, shaping the overall cycle of matter between stars. Detecting them is difficult because they emit very little radiation, yet faint signals in the infrared and radio bands hint strongly at their presence. These silent storehouses of ancient material serve as archives of cosmic history, preserving crucial clues about the conditions that shaped the earliest environments in the galaxy. They are time capsules of cosmic chemistry. There might be complex magnetic fields spanning vast distances. The galaxy is threaded with intricate magnetic fields that twist, bend, and interact with charged particles. These fields are notoriously difficult to map directly because they don't emit light themselves. Instead, they reveal their presence through the behavior of cosmic rays, the polarization of starlight, and the subtle motion of gas clouds. Some regions show remarkably coherent magnetic structures extending through interstellar space, suggesting large-scale organization. Others display tangled patterns shaped by turbulence or the shock waves from exploding stars. These magnetic fields profoundly influence star formation, guide the paths of charged particles, and help regulate the temperature of interstellar gas. They may also shape the boundaries between different regions of the galaxy, creating large but invisible frameworks that affect how matter moves. Understanding these complex magnetic structures is essential for accurately modeling the behavior of the interstellar medium. Yet, many details remain unknown. Their sheer complexity points to underlying processes that span enormous distances and incredibly long periods of cosmic time. There could be waves traveling through space that we haven't yet recognized. Beyond gravitational waves, which are ripples through spacetime itself, there may be other forms of waves moving through the galaxy. These could arise from oscillations in magnetic fields, fluctuations in charged particle densities, or variations in interstellar pressure. Some may travel slowly through diffused gas, while others might move rapidly across regions filled with plasma. Because they don't emit strong light directly, they are difficult to detect with traditional instruments. Their presence could influence the formation of stars, the behavior of cosmic rays, or the distribution of material across the galaxy. Detecting these waves would require sensitive measurements of radio emissions, polarization patterns, or tiny changes in the motion of interstellar gas. Discovering such hidden waves would reveal new channels through which energy flows across vast cosmic environments, adding significant depth to our understanding of galactic dynamics. It's a hidden symphony of cosmic vibrations. Exotic molecules may form in interstellar regions where chemistry, by all accounts, should fail. Some areas of interstellar space are so incredibly cold and diffuse that chemical reactions should be extremely slow, almost non-existent. Yet, observations reveal complex molecules that seem far too intricate to form under such barren conditions. These exotic compounds range from simple organic molecules to surprisingly complex structures. They may arise from reactions occurring on the surfaces of tiny dust grains, triggered by faint starlight or cosmic rays. Alternatively, they might form within transient pockets of denser material that collapse and disperse quickly. The presence of these unexpected molecules challenges traditional ideas about where and how chemistry can occur in the universe. Their distribution influences the composition of forming stars and planets, seeding young systems with raw material that may play crucial roles in later chemical evolution. Understanding how these unexpected molecules form requires a combination of laboratory experiments, sophisticated modeling, and careful astronomical observation. Their existence highlights the incredible creativity of nature, even in environments once thought chemically inactive. There might be unseen objects passing through our solar system. Our solar system is incredibly vast, and many of its regions remain poorly explored. Objects with extremely dark surfaces or unusual compositions could drift through its outer reaches without reflecting enough light to be detected by our telescopes. Some may follow long, looping orbits that keep them far from the Sun for most of their journey. Others might pass through our system only once, moving quickly and silently before returning to interstellar space. Their gravitational influence on known planets or comets might be too subtle to measure with current technology. Detecting such unseen bodies would require wide, field surveys capable of spotting very faint movement against the background of stars. Future missions that map the sky continuously may finally reveal these hidden travelers. Their discovery would expand our understanding of the solar system's population and shed light on the variety of objects that wander through our celestial neighborhood. It's a cosmic game of hide and seek with our solar system as the playing field. The nature of quantum vacuum energy remains a deep mystery. Empty. Space is not truly empty. According to quantum physics, even the quietest vacuum contains a restless sea of energy that simply cannot be removed. This vacuum energy influences how particles behave and how fields interact. Yet, its true origin remains unclear. Calculations of vacuum energy often produce values far larger than anything observed in the real universe, suggesting that something in our fundamental understanding is incomplete. This energy might interact with space in ways that affect cosmic expansion, hinting at a possible connection to dark energy. It could also subtly shape how quantum fields fluctuate across vast distances. Because vacuum energy cannot be switched off or isolated, it can only be inferred indirectly through subtle measurements of particle behavior or delicate shifts in atomic states. Every attempt to explain it opens new questions, suggesting that vacuum energy may hold crucial clues to deeper layers of reality that lie beyond current theories. It's the silent, energetic hum of the universe. Particles might pop in and out of reality from hidden realms. Quantum theory allows particles to appear briefly, interact, and then vanish again, essentially borrowing energy for a fleeting moment before conserving the total balance. These ephemeral phenomena are usually described as quantum fluctuations. Yet, some researchers explore the intriguing idea that they may be linked to realms outside our ordinary space. In these views, particles could momentarily dip into hidden layers of the universe before returning, creating short-lived, subtle signatures in measurable quantities. If such realms exist, they could host structures or fields that influence our world only through these brief, transient interactions. Detecting these events directly is nearly impossible because they occur on unimaginably small scales and over extremely short intervals. Instead, scientists search for tiny deviations in particle collisions or unexpected patterns in the behavior of quantum fields. These fleeting appearances hint that the universe may include unseen dimensions or hidden layers that leave only the faintest traces on our observable reality. It's a quantum dance with unseen partners. Quantum processes could influence the entire cosmos. While quantum physics typically governs the world of the very small, some of its processes may have effects that ripple through the universe on enormous scales. Fluctuations in quantum fields during the earliest phases of cosmic history might have seeded the large-scale structure of galaxies. Tiny, random variations could have grown over cosmic time into the massive clusters and vast voids that are visible today. Quantum tunneling might also play roles in processes that affect the lifetime or evolution of the cosmos itself. Even the long-term stability of space could depend on quantum interactions occurring throughout the vacuum. These possibilities suggest that the behavior of particles and fields on minute scales can profoundly shape the universe's ultimate fate. Understanding these influences requires bridging the vast gap between quantum theory and cosmology, two domains that operate under vastly different conditions. Their intersection remains one of the richest and most mysterious areas of modern physics. It's where the smallest bits of reality shape the largest structures. We don't know whether reality is continuous or pixelated. Mathematics often describes space and time as smooth and continuous, like an infinitely divisible fabric. Yet, some theories propose that at the smallest possible scales, they might instead be composed of discrete, tiny units. These tiny, building blocks could determine the limits of how finely space and time can actually be divided. If reality is indeed pixelated, then fundamental notions such as position, motion, and energy may behave differently near these incredibly fundamental scales. Experiments that probe extremely short distances or incredibly high energies are necessary to test this idea. Yet, achieving such conditions is far beyond our current technology. Indirect hints may come from the behavior of gravitational waves or from subtle anomalies in the motion of particles. Determining whether the universe is fundamentally continuous or discrete would completely reshape our understanding of geometry, physics, and the very nature of spacetime. It remains one of the deepest unanswered questions in theoretical science, challenging our most basic assumptions about reality. The universe might be haunted by virtual particles we cannot observe. Virtual particles constantly influence measurable properties, even though they don't appear in ways detectable as ordinary matter. They modify forces, subtly shift energy levels, and alter how real particles interact. These unseen contributors arise naturally from the quantum fields that fill all of space, flickering into temporary relevance only during specific processes. Though they vanish almost immediately, their effects accumulate across countless interactions, subtly shaping everything from atomic transitions to the behavior of electromagnetic fields. Virtual particles may also play crucial roles in more mysterious phenomena, such as the vacuum energy problem or the behavior of space under extreme conditions. Their existence reveals that much of reality operates through hidden processes that can be inferred only through their influence on observable quantities. Understanding them forces physicists to accept that unseen layers of activity fundamentally underpin the physical world we perceive. It's a constant, invisible hum of activity that shapes everything. Quantum fields could be more fundamental than space itself. Some interpretations of physics treat quantum fields as the primary, most fundamental ingredients of reality, with particles emerging as mere excitations of these fields. In this view, even space itself may not be a fixed, unchanging stage, but rather a phenomenon that arises from deeper interactions among these fields. The geometry of the universe, the strength of fundamental forces, and the behavior of matter could all be consequences of intricate patterns embedded within these quantum fields. If this perspective is correct, then space might not exist independently. Instead, it would emerge from complex relationships among more basic components. Evidence for this idea appears in attempts to unify gravity with quantum theory. Some approaches suggest that space-time curvature reflects how information or entanglement is distributed within quantum fields. Uncovering the precise structure of this deeper layer remains an enormous challenge. Yet, its implications would utterly transform our understanding of the universe and the very nature of reality. Quantum uncertainty might shape the large-scale structure of the universe. Quantum uncertainty dictates that particles cannot have perfectly defined positions or energies simultaneously. During the universe's earliest moments, this inherent uncertainty created tiny irregularities in the distribution of matter and energy. Over vast cosmic time, gravity then amplified these incredibly small irregularities, causing some regions to grow into the galaxies we see today, while others became the vast, empty voids. Thus, the overall structure of the universe, with its intricate cosmic web, may owe its very shape to random fluctuations that occurred at quantum scales. Even now, quantum uncertainty may continue to guide processes such as the behavior of black empty or simple. The space between stars may be a vibrant and evolving environment, a cosmic ocean full of hidden depths. As we gently drift to the end of our quiet journey, take a moment to truly feel how incredibly wide the universe is. Every single mystery we explored tonight is a profound reminder that our understanding is still very, very young. Even after all the amazing discoveries that science has made, so much remains completely hidden in the deep, dark spaces between the stars. It's like looking at a vast, ancient map where most of the territories are still marked, unknown. Every unanswered question we've touched upon is like an open door, inviting us to look further. Every strange signal, every unusual pattern we've discussed, is a quiet invitation to examine things even more closely. The unknown is not something to be afraid of. Instead, it's a boundless landscape that continues to grow, to unfold, and to reveal itself to us as we learn more. It stretches out endlessly, always offering new wonders to contemplate. We've talked about the unseen boundaries of our cosmos, those regions whose light will never reach us. We've imagined realms where the fundamental laws of physics might play out in entirely different ways, creating universes we can barely conceive. The very origin of time itself remains a profound enigma, a moment shrouded in the deepest cosmic mists. And the true shape of space, whether it loops back on itself or stretches into infinity, continues to be a question that humbles our grandest theories. We considered the possibility of invisible dimensions, curled up so tightly that they exist within every point of our familiar space, whispering subtle influences. And we pondered what space itself is made of, challenging the idea that it's merely an empty stage. Perhaps it emerges from a deeper, more intricate fabric of reality. The variable flow of time across the universe, affected by gravity and motion, reminds us that, no, isn't a single, fixed moment for everyone, everywhere. And the captivating idea that our universe might just be one bubble among countless others in a grander multiverse expands our cosmic neighborhood far beyond what we typically imagine. We've wondered about colossal structures that might exist beyond our current observational horizon, quietly shaping the cosmos we see. And the question of whether the universe has an actual edge or expands into an unseen outside keeps our minds stretching for answers. The remarkable smoothness of space on vast scales, a puzzle known as the horizon problem, hints at processes that unfolded in the universe's earliest infancy, smoothing out irregularities before they could take hold, and the subtle imprints that might remain from events before the Big Bang itself suggest a cosmic history that began long before our familiar expansion. The cosmic web, with its intricate patterns of galaxies, might hold hidden symmetries we've yet to decode, revealing a deeper order. And the myriad ways the universe might end, from a cold, empty expanse to a dramatic, big rip, or a fiery, big crunch, remind us of the cosmic clock's uncertain future. We even touched upon the idea of cosmic cycles, where universes might repeatedly contract and expand, creating an endless rhythm of creation and destruction. The mysterious trigger of the rapid early expansion, known as inflation, remains a key to unlocking the universe's primordial secrets. And the notion of hidden dimensions, too small to see, suggests a richer, multi-layered reality. We explored the possibility that space is not fundamental, but rather emerges from a deeper, underlying structure, perhaps from quantum information itself. This leads to the mind-bending idea that our universe could be a holographic projection of a lower, dimensional reality. We also delved into the enigma of dark energy, wondering if its strength changes over time, shaping the universe's accelerating expansion. And dark matter, that invisible scaffolding of the cosmos, might be composed of particles completely unknown to physics, or even be a shadow of processes occurring in higher dimensions. We considered the silent parade of undetected particles constantly passing through us, and the potential for dark matter to form complex structures mirroring our visible universe. Dark energy might even subtly interact with matter, a hidden dialogue we've yet to observe. And the idea of multiple types of dark matter, a rich, dark sector, suggests a hidden diversity. We imagined entire stars made of dark matter, and how dark matter itself could be a cosmic archive, holding clues to ancient eras. Black holes, those ultimate cosmic prisons, may contain regions where reality breaks down, or their centers might be something other than the predicted singularity. The fantastical idea of paths through black holes leading elsewhere, and how they might store information in ways we don't understand, keeps our imaginations alight. Tiny primordial black holes, relics from the universe's birth, could still be drifting unseen. And the event horizon, the black hole's edge, remains a quantum mystery. The slow, unobserved evaporation of black holes and the possibility of black holes forming before the first stars paint a dynamic picture of these cosmic behemoths. We even learned how black holes shape galaxies on grand scales and considered the possibility of silent, hidden black holes. Finally, we looked at gravity itself, how it might behave differently on vast scales, or whether hidden forces influence distant galaxies. We thought about gravity's link to quantum information, and the potential for gravitational phenomena we haven't even conceived of. We wondered if gravity's strength varies, or if it leaks into other dimensions, or if its fundamental constant isn't truly constant. The unknown workings of gravity at the universe's birth, and the hypothetical particles that mediate it, all point to a deeper understanding yet to be achieved. And the idea that gravity emerges from something more fundamental than spacetime itself challenges our most basic assumptions.